Okay, so this is the just continuation of 1.8. So we're just going to do a few more exponent laws. So let's just extend what we know from the exponent laws here, just to see if we can expand and simplify some complicated expressions. Okay, so what happens if I have 2 times x cubed times y squared in brackets, and all of that raised to the power of 4? So let's write this in expanded form. So in expanded form, I'll be writing this bracket 4 times. So 2x cubed y squared times 2x cubed y squared times 2x cubed y squared, and one more time, 2x cubed y squared. Okay. So it turns out if I separate the 2's, the x's, and the y's, it looks like I have here, if I have a 2, put that in brackets. How many 2's do I have? I have here a, let's just get my cursor on the screen. So I have here 2, 4, 1, so 1, 2, 3, 4, 2. So 2 to the power of 4. And then I'm going to write here x cubed. How many x cubes do I have? So I have 1, 2, 3, 4 again. And the y squareds, how many y squareds do I have? Well, again, I have 4 of those. Oh, let's see. Interesting, huh? All right, so let's simplify this a little bit. So 2 to the power of 4, I can evaluate this. So that's 2 times 2, which is 4, times 2 is 8, times 2 is 16. So in simplified form, I'm going to write here 16. X cubed to the power of 4, so these two here. 3 at the power, it's the power law, so one exponent raised to another exponent. So 3 times 4 is 12, so I'm going to have x to the power of 12. And then I have y squared to the power of 4, so these are, again, power law, exponent raised to another exponent. So 2 times 4 is 8, so y to the power of 8. Okay? Now, so you notice I've simplified it, so just 16, my coefficient, x is my base here with the exponent 12, and then y is my next other base here with the exponent of 8, and all three are being multiplied with each other. Okay, I can't combine them anymore because these are all different bases. X and y are different bases. Let's have a look at another one. So now you might get and sort of understand what's going on here. What's happening is I'm distributing this exponent 4 with each of the exponents on the inside. Okay, so you think about 4 going with that 2 there, going with 3, and going with the 2 over here. So that exponent just gets multiplied with everything that you see here. There's a visible exponent of 1 here with the 2. So it's 1 times 4, 3 times 4, and 2 times 4, which gives me 4. So that gave me the 4, 12, and 8. Okay, so I can do the same thing for the next one. For the next one, I'm going to have here negative 3 to the power of 3. I'm going to have x to the power of 3. And here I'm going to have y to the power of 4 raised to the power of 3. Okay? And if I simplify that, well, negative 3 times negative 3 times negative 3 is 27. Negative 27. Remember, 3 negatives make still a negative. So negative 27. And x cubed. Remove the brackets from that. And y to the power of 4 to the power of 3, multiply the exponents, it's power law. So it's going to be y to the power of 12. Okay? So what's the rule? Exponent applies to every part of the term. So the term is this whole thing, and every part of the term are these numbers, so negative 3, x, and y. Right, so the exponent has to apply to every part of the term. So let's try these out. So 4xy cubed to the power of 2. So this exponent has to apply to every part of this term. So it's going to be 4 squared, x squared, and y to the power of 3 raised to the power of 2. Okay, so 4 squared is 16, x squared is just x squared, and this last one here is y to the power of 6. What about this complicated expression? Interesting. So first apply the exponent. So I'm going to have negative 2 to the power of 2, x cubed to the power of 2, and y squared to the power of 2. And don't forget, you're still multiplying by 3xy. Okay, so negative 2 squared, negative 2 times negative 2 is positive 4. X to the power of 3 to the power of 2 becomes x to the power of 6. And then y squared to the square becomes y to the power of 4. And don't forget, you're still multiplying negative 3x and y. Now, x and y have an invisible exponent of 1 and 1. Okay, so now when I'm multiplying parts of these terms, I'm going to multiply the coefficients first. So 4 times negative 3 gives me negative 12. X to the power of 6 times x to the power of 1. Again, I can only multiply these because these have the same bases. Okay, so x to the power of 6 times x to the power of 1. I'm going to add their exponents, so 6 plus 1 is going to give me x to the power of 7. And y to the power of 4 times y to the power of 1. I'm going to add their exponents, 4 plus 1, which is 5. And then there's my answer. Okay, perfect squares. What is a perfect square? Well, here's some examples. It's a number that looks like this. So 3 squared, 3 times 3 is 9. And so 9 is a perfect square. 4 squared, so 4 times 4 is 16. 16 is a perfect square. Okay, so I want you to pause the video for a moment and try and find the perfect squares for each of the following. Okay, so if you've done that, here are your answers. So 25, 36, 49, 64, 81, 100. Okay, so these are all perfect squares. These are numbers that can be written as a square of one of its factors. Okay. So given the following integers, indicate which of the following is a perfect square. What is the opposite of a perfect square? Well, it turns out it's the square root. So if you can find the square root of a number and you get a nice, nice integer, okay, no decimals, that's going to be an indication of a perfect square. So what are they? Well, 25, the square root of 25 is 5, so I'm going to say this is a perfect square and circle that. The square root of 64 is 8, so I can circle that, so 8 squared is 64. 225 is also a perfect square, which is 15. So square root of 225 is 15. Square root of 81 is 9. 9 times 9 is 81. Square root of 121 is 11. 11 times 11 is 121. 196 is another one. And 1024 is another one. 169 is another one. Square root of 169 is 13. And 1, it's also another one. So square root of 1 is still 1. That's a perfect square. Okay. So these other ones don't work. So you try them out yourselves on your calculators to see what you get. Negative 4. So these negative numbers, these don't count. Okay. So why? Because there is no, I can't take the square root of negative 4. The square root of negative 4 is what we call in mathematics an imaginary number. There's a definition that the square root of negative 1, so again, negative 1 is not a perfect square because you can't do it. It's not defined as a real number. So we call it an imaginary number. We give it a special letter and call it I. So we're not going to be using imaginary numbers in this course, but just so that you're aware of what's happening. Square root of negative 1 is an imaginary number. So again, there's no other way of looking at it. I mean, if you do 2 times 2, it's positive 4. If you do negative 2 times negative 2, that is also positive 4. There is no same two numbers that I can multiply to give me give me a negative 4, unless we're going to be doing imaginary numbers. So we're not doing imaginary numbers. Okay, so moving on. Rewrite. Well, actually, one more thing before I stop. Let's look at 0. Okay, I want you to think about 0 for a moment. Is that a perfect square? You probably have to do a little bit of research on that on your own, but there's going to be a good answer for that one. And we could talk about that one in class. Rewrite each of the following numbers as a power. Okay, so 49 can be written as 7 squared. Just take the square root. Right? So take the square root. The square root of 49 is equal to 7. Coincidentally, it's also equal to negative 7. Why? Because negative 7 times negative 7 also equals positive 49. When you get to grade 10, You have to know how to do get two answers from a square root like this. Okay, but for now, 7 squared is fine to save as my one answer for this. If we do need to do this later, I'll let you know. All right, so 729. So this is not one that you can just square root. You kind of have to look at a different kind of, what number can I get to that 729? Well, you can do multiple ways. 3 to the power of 6 gives you 729, or you can do 9 to the power of 3, which gives you 729. What about 216? Well, 216 is 6 to the power of 3 works. Yeah, that's a possible answer. Um, but it's not a perfect square. Okay, but you can still express 216 as a power. You can also express 16 as a power as well, which is 4 squared, or even 2 to the power of 4. There could be potentially more than one answer. All right. Now, how do I know to come up with these numbers? Right? How do I know 729 can be written as a power with the base of 3, or power with the base of 9? Well, that comes from divisibility rules. Okay, so if I know 729, I would know that 729 is divisible by 3, and I also know that it's divisible by 9. How do I know? Well, there's some divisibility rules. Um, I'm going to do so. I didn't write them in here, but basically it says that if a number is going to be divisible by 3, then the sum of the digits should be divisible by 3. So what are the sum of the digits? So 7 plus 2 plus 9, well, that's 18. So 7 plus 2 plus 9 is equal to 18. And I know 18 is divisible by 3, so if I divide by 3, I get 6. So I know it's divisible by 3. So I'm just going to be looking for an exponent that 3 to the power of something gives me 729. Okay. How do I know it's divisible by 9? Well, there's a special rule for that. The sum of the digits also has to be divisible by 9. So 18 is also divisible by 9. 18 divided by 9 is equal to 2. Okay. All right. 216. Well, how do I know that 6 works as my base? Well, if a number is to be divisible by 6, then the sum of the digits of 216 have to add up and be divisible by 3. And so 2 plus 1 plus 6 is equal to 8. Okay. And just